And inductance is just exactly what it says, induced. So current is induced by a voltage. A voltage is called electromotive force. It is a force, and it pushes the electrons. But voltage never goes anywhere. It doesn't move. It's a pressure. It's a relationship. It's a relationship between a lot of electrons and not a lot of electrons. Okay? For in DC, it's easy to understand. The electrons go to where there's no electrons. And that's current. Voltage is the relationship between how many electrons you have and how many electrons you don't have in the other place. That's your pressure. That's your head of water. Okay? So as the current is trying to go through this coil, it's creating a magnetic field. That magnetic field is expanding. When it's expanding, it's cutting those wires. Okay, by cutting it, I mean it's interfering with these wires. When it interferes with when a magnetic field interferes with a wire or any kind of conductor, it creates a current. Now, because this magnetic field is in this way from the induced or the coming in current, the induced current is in the opposite direction because the field, generating field, is opposite. That concept is very difficult to understand, but you'll have to take my word for it. That's what it does. And by doing that, that's slowing down the current, right? And my relationship here is that the current is 90 degrees out of phase with the voltage. So when the voltage is when the current is at maximum, the voltage is at zero. Odd, but that's exactly what happens. And this ends up being like a resistor to AC. A capacitor, on the other hand, is two plates that don't touch. DC cannot pass through a capacitor because there's no connection. But AC, because it pushes all the electrons away from this side, and then in the next cycle, it pushes all the electrons away from this side. So it's going to go through the capacitor, right? Because it's alternating between them. When we put two of them together, now we have the current lagging and leading and whatever. But at some point, when the capacitance and the inductance, I had the resonant one here a minute ago, because resonance is what's important. Oh, I mixed things up. Yeah, see, this wasn't on the thing either, and you're going to need to know this. We'll still stay with the inductor. There's the winding has resistance. There's also magnetic leakage. Magnetic leakage is the lines of force don't actually, they're on the other side, so they don't cut the field once it out. Some of that will be lost. Hysteresis. As the magnetic field is changing back and forth, it gets over here, but all of a sudden it's got to be over there, and it didn't quite get finished going over here. There's a loss there. Okay, so it doesn't get, and that's all this timing thing. You can read that in the notes, and you should be able to understand. Now, resonance is a different situation, and he wrote this thing on here when the things are in resonance, which is very important. What the hell did I do with it? Sorry. Okay, we still have to understand inductive reactance and capacitive reactance. Inductive reactance is just the inability of this thing to take power. As the frequency increases, so does the reactance. In a capacitor, the exact opposite happens. As the frequency increases, the capacitance goes up. Yeah. So when they balance out in this parallel circuit, we have what is called resonance. Too much stuff here. There's a parallel resonant circuit. And then, in order to talk about resonant circuits, you got to talk about Q. Well, Q is just what it says. It's quality. But it's the... in a resonant circuit, energy is stored alternately in the electric field of the capacitor and the magnetic field of the inductor. Exactly. So we have this. Can we find the parallel one, please? There. So we have an electric field, a magnetic field, and electric field. So this is bouncing back and forth, and there comes a point where they're equal, and what comes in here comes out there. But up to that point, very little gets through. There will always be some, but it's very little. Now, as we tighten these up, we can change the Q factor. The Q factor is the circuit. Okay, the relatively high circulating current. Oh, yeah. Okay, so it becomes almost a dead short, so you have maximum transfer of energy. But all the other energy at other frequencies gets held back because it can't resonate. I got myself into a serious situation here where this came up before I got through all of the stuff that we needed to talk about. And are you convinced that you understand what reactance is? Capacitive reactance and inductive reactance. And that relationship they're completely opposite. Okay? So as the frequency increases, the reactance here increases, but it decreases here.
So one is inductive, the other one is
Capacitive.
capacitive. Which one is capacitive?
This is the capacitor.
Okay, that's what I thought.
So it's capacitive reactance. So as the frequency increases, this one gets more capacity. This one gets less capacity.
Now, what's it called when they? Oh, it's
Less,
called.
more resistance rather. Sorry.
When you get an example of both and put them on parallel like this, what is that reaction called? That's called
Resonance.
Resonance. Okay.
If they equal out, but it'll only be resonant at a particular frequency.
So is that kind of like a relay switch, like where it all of a sudden kicks on?
No,
Okay, I was just curious.
no, that's a solenoid, and a solenoid is just an electromagnet,
Right.
and a solenoid is slow at the start, but as the armature gets into the coil, it picks up speed
So I guess my question.
because the magnetic field becomes stronger.
My question really should have been, is at what point do we do this? Why are we doing this?
Well, that's
I'm gonna try something on if you don't mind, real quick. Right, okay, everybody knows the stereo system. Let's say you want the highs to come out, the high frequencies.
All right, so I want to put it.
So what you would do is you would set that, the resonance there at the high frequencies by adjusting your capacitance or your little knob.
Yeah.
You're adjusting that resonant frequency that is tuned for, so it'll only allow the highs to go out.
Okay.
Okay? You can also adjust it the other way to make only the lows come out.
if you see these and it has an arrow through it, means it's a variable capacitor. Same thing with this guy. And we do vary inductors and we do vary capacitors. And we change the frequency because we only want a certain frequency to get through this circuit. So by tuning a station, I'm going to tune that capacitor so that only that frequency for that station comes through and it rejects all the others.
So this form, or that diagram is very important to radio work.
Oh yeah, that's the whole basis of radios.
Right. Right.
there.
Yeah. Now, the quality of this circuit is called the Q factor. And I was just trying to make sense out of this. How effective a tuned circuit will be in selecting only a narrow band of frequencies. So that will depend on the quality of the materials and also how much resistance is in the circuit. The resistance will tend to broaden the band of frequencies that can come through. No filter will give you just, no mechanical filter like this will give you just, because there's so many factors that are affecting it. The temperature of affects the temperature of the materials. Everything is in an effect, okay? So we make our filters fairly wide to allow a certain number, and then we have other ways of getting rid of the noise, getting rid of this stuff. But the whole point of this is to understand that we have inductors and we have capacitors. Inductors restrict the flow of AC, capacitors inhibit the flow of DC, okay? But both are used in AC to create this filtering thing by using the thing called resonance, and that the resonant frequency of that will be determined by the capacitive reactance and the inductive reactance when they are at the values which gives you that. So allows the thing to pass. And that's because the energy is stored in the magnetic field and it's stored in the electric field. Okay, we store electricity here, we store current here, we store electrons here, we store magnets here, basically. So the magnetic field is the big thing about inductors, is that expanding and contracting magnetic field. Now the type of inductors that I work with are called motors. Motors have big inductors in them. Okay, they're big coils of wire. And it's all the same, it's the same there. We have this thing about leading and lagging. This is very important. In an AC motor, the current lags the voltage. Okay, so if all of your loads in your mill are AC motors, then you are paying for power you're not getting. Because like I said, this is all the power you're actually able to use. There is no power here. There is power here, or here rather, sorry, just under that curve, or right here rather. Just under the curves is power. This is lost power. So what we do in industry is we take a capacitor. What happens in a capacitor? The current leads the voltage. And it's the same relationship, only this would be the voltage and this would be the current in a capacitor. Okay? So if I put these two together, what can I do? I can move that so that it's in phase with that, and that's called resonance. Once they're in resonance, then the maximum amount of current will flow. Okay? So I'm altering the frequency. And I can do that because this one, the current is leading the voltage, and this one, the current is lagging the voltage. So when they come out here, son of a gun.
So
together.
if you have control over both, you can control the,
Well, you only need to control one because
you just have to set
this
them up.
factor is always going to be the same. By changing this, you're going to change the frequency at which it can happen. Okay?
Okay.
You can control both, but you can get into a situation where you end up with a dead short in your inductor, and then you'll have a real big problem. Because you start moving and, oh, I'm getting down close to the bottom. If you stayed up there and you just adjusted this one, and you would, I think we get a better understanding now, right?
I do.
It's all about asking questions. And every time when I teach, the first thing I tell people is there's no stupid question except the question that isn't asked. Because you ask a question and it leads to something else. And we all learn at different rates and we all learn in different ways. Okay? Sure.
When it gets there, when it syncs up like that, that's my understanding is that's when a clear signal comes in or goes out. Am I wrong? Is that what resonance is?
Say again?
Is that what resonance is? When it syncs up like that, the clarity and power goes out, or?
Well, what is actually happening here is this is resisting the flow of AC. This is not resisting the flow of AC. But it's only resisting the current. It's not resisting the voltage. The voltage is there. There's a voltage between here and here. But at a certain frequency, these two will help each other to put that back in sync. So only that frequency can come through. So no matter what frequency I put up here, only that frequency will come through.
Like 99.5.
99.5, a good example.
Okay.
So I tune my capacitor to 99.5. You don't hear 98.3. You don't hear 100.5. You only hear whatever one it was you said.
And Mike, the variable change.
Yeah, I didn't have a variable capacitor to bring in, so I couldn't.
Is that what allows you to pick up more than one different frequency?
Well, the wider the bandwidth of this filter, the more frequencies you'll get. Now we have to have a certain width for FM, and then we have to have a certain width for AM. AM's generally narrower. Okay.
So you can get resonance at all of the different frequencies by adjusting.
Yes.
One of the.
That's the whole purpose of this lecture, is about how the inductor slows the current and the capacitor speeds the current. So now we bring them into sync, we have resonance, and because we looked at those formulas which showed you inductive reactance and capacitive reactance, they're on opposite directions, correct? Inductive reactance is 2 pi FL, right? And inductive capacitive reactance is 1 over 2 pi FC. Okay, so in capacitive reactance, if I change the frequency, okay, the number is smaller. In this one, if I increase the frequency, the number is smaller. In this one, if I increase the frequency, the number is bigger. So the reactance is more, the reactance is less. So I get to a point where they cancel each other out, and boom, the whole signal goes through. Right? There's a formula for that in these notes. Give me the next one, I think. Oh, this is the thing about Q, about bandwidth. Okay. The bandwidth of a tuned circuit becomes narrower as the Q increases. Okay, so this is the narrower bandwidth. You can see this one is lower. Allowing us to use this type of resonant circuit to select one frequency. Yeah, that's the whole point of resonance, eh? Give me the next one, please.
I think that's it.
Okay, so back up until we get some more formulas here. Okay, that one there. That's the formula for resonance. So we can figure out resonance.
So can you go through what each of the initials, or what each of the letters?
This is resonant frequency.
Okay.
This is 2 pi times inductance and capacitance, square root of inductance and capacitance. I'm not sure if this formula is actually correct, but it probably is. These have to be in the right units, that's the word. I had a really serious motorcycle accident in the spring and I have some brain damage. I lose words, so that's what's happening here.
On the exam, you won't be asked to calculate impedance. It's very rare that you are asked to calculate reactance. Once in a while, you have to calculate resonance, but it's pretty rare.
Well, just be aware of the relationship. The other ones, keep going back. I get some other formulas here. This is impedance.
Yeah, you won't be asked that one.
Well, okay, this is resistance and reactance. Okay, go back. Okay, this is the one you're going to need to know this one. Okay, that's capacitive reactance. XC. X is reactance, C is capacitive. Okay, so you can see the relationship is an inverse relationship. So whatever happens on the bottom makes the number smaller or bigger, depending on which way you go. Eh? So if you increase this value or you increase this value, this number gets smaller. If you decrease this value or you decrease this value, that number gets larger. Okay. Go back one more, please. In the inductive circuit, the inductive reactance, if you increase the frequency, the inductive reactance gets larger. If you increase the henries, the inductive reactance gets larger, and if you reduce them, they get smaller. So in our resonant circuit, you can see that's what we're tuning. We're tuning that reactance till we get to the point where these two guys come together. So you can see that you actually, all the time you're getting something through that circuit. But the point is, when we get in resonance, we get the most through. And that means it's louder than the other, and we can chop the other stuff off. That's just capacitors in parallel. The more capacitors you have in parallel, you just add them up, because that's more capacity, right? You can see it. The drawing shows you. The same with inductors. When they're in series, they add up because you have more inductance. When they're in parallel, you have less inductance. Okay? Because inductance is magnetic field strength. That's where what inductance does. It gives you the magnetism. It gives you the power. All electricity and magnets are very, very interesting. And understanding how they interact is phenomenally interesting. And we as and even scientists are not 100% sure how this actually works, because current is energy. Energy. What is energy? Energy is motion, basically. Because when you get down to absolute zero, which is minus 273 degrees Celsius, there is no energy there is no motion. Nothing can move at absolute zero. That's the theory, because we haven't reached absolute zero. So now you can see temperature is going to have an effect on this too. This is old school, like we used to do this for selecting frequencies and stuff. Nowadays we use electronic circuits to create our frequencies and to filter our frequencies. My cousin owned a company that developed filters, which was what these are, for the aerospace industry. And the stuff you're learning is the same stuff he uses to calculate his filters. Okay? On a bigger scale, because there's more components involved and more to it. But basic idea, resonance. Only that one frequency we want to come through. Okay? You catching on? Oh. I don't want to leave anybody behind. I don't want to confuse you.
So
I wanna
if you
help
know
you.
the frequency you want, and you know the,
Yes, you can calculate.
your inductance, you can algebraically solve for the capacitance that you need.
Yeah, that
Yes, to design your circuit, yeah.
FR
You can design your circuit.
is the square root of 2 pi. No, 2 pi times the square root of L plus C, or LC. Henry's times capacitance, Henry's times farads. Whenever you're doing your calculations, it's very important to get your units correct. So the best way is to use the decimal point. So if you have 10 millihenries, that's 0.010 henries. Okay, I think. 2 zeros.
0.001
is 1 millihenry.
Pardon?
Yeah, but you had 10 of them.
0.001 is 1 millihenry.
I said 10 though.
Or 10?
10 millihenries is 0.010.
Yeah.
So you just write that into your formula, and that way you'll be correct. Same when you get into microhenries, then you got to put the other 3 zeros in there. Capacitors is really hard because they're in the negative. Oh, yeah, they're the same, but they're much smaller. They're nanofarad, picofarad. Okay. I don't know what else I can.
One place
That
where
is-
you use this, Ron, and most people are not going to be building, building radios and, building tune circuits and make the radio. And one place you're going to use this, and when I teach antennas, I'm going to bring this up, is you're going to use that tune circuit for what we call a trap dipole. And the traps, yeah, you could use that as a trap. And
They'll usually have a core though.
the trap has a parallel circuit, and what it does is it only passes the RF frequency. It only passes at a certain frequency, so automatically, let's say you're on the 40-meter band, and it'll block the ends of the antenna off, because it won't go to the 80-meter band. So the ends of the antenna are blocked, the antenna is shorter, it works on the 40-meter band. But when you switch to the 80-meter band, because it's resonant on that frequency, it'll pass that frequency, and all of a sudden your antenna is working on 80 meters. So you got one antenna with these traps on it, those parallel tuned circuits, that it becomes a multi-band antenna. You see, it's just one antenna.
Yeah.
So that's what's the use. That's what we make our own coils and put the capacitor, and you test it yourself. You can put the thing up, and away you go.
We also use these things for impedance matching,
Yes.
for matching our antennas. And the best example of an impedance match is now out of date. But at one point we used to use twin lead into our television sets, and the rabbit ears and stuff. But you guys probably don't even remember that. And you used to get this little thing about this long, and it had the 2 leads coming out that went to the antenna, and then you screwed the coaxial cable into it. That's called a balun, a balanced, unbalanced device. All it is,
Upgrade mine with the foil.
what that actually is an inductor. Okay, and that's changing, or a transformer. I'm sorry, transformer, and that's changing from this impedance to that impedance. 300 ohm for the twin lead, 75 ohm for the coax for your television. Now we use HDMI cables and all kinds of crap. But in our field, in ham radio, our output impedance is 50 ohms. You still can use the dipole antenna, which has a theoretical 300 ohm impedance. So we have to match that. And once again, we use a matching transformer, which is just a pair of inductors. So it's important to understand what induction is and what capacitance is. And the words tell you what they are. Inductance is inducing. And it's that counter EMF is the most important thing. So as the current goes this way, it's creating a current coming this way, which is restricting it. And that's why it goes out. Okay? And that has to do with the magnetic lines. Because the magnetic lines are expanding as the current increases. Because the more current, the stronger. Oh, that's what I meant. That's one thing I forgot. The number of turns on a coil determine the strength of the magnetic field. The amount of current through that coil determines the strength of the magnetic field. So if you want to make the field stronger, you can put more turns or you can put more current. In order to put more current, you need more voltage. Bigger wire. This is pretty big wire.
What was that off of, Ron?
Shock.
A 6-band vertical.
That's good for 30 amps.
9-band vertical.
Like a, with a comet or a?
No, I forget the name of it.
Butternut?
Butternut.
But off the butternut, okay.
Yeah.
That's what it looked like.
That's good for 30 amps, Ron.
This year?
It's about the dryer plug.
No, it's,
30 to 40 amps,
that's number 6 wire.
100 amps.
100 amps, yeah.
We're never gonna get our amperage up that high.
You'd be surprised.
On RDF?
You'd be surprised.
By accident, yes.
Oh, that's another thing. Before I forget. As we increase in frequency, less and less of the current travels through the wire. The current gravitates to the exterior of the wire. So the higher the frequency, the more of the current flows on the outside of the wire. And to the point where we get into microwaves, microwaves for radar, that's what I was going. We use a thing called a waveguide, and that current is going in a guide that goes through the air. Very interesting stuff. You can get very severe burns from radar.
Burns from antennas.
Yeah. Yeah, don't grab an antenna. Well, I would appreciate if you ask questions or if you tell me whether you learned anything or this is the point where
Picked up a lot today.
Yeah.
Yeah.
Yeah, but you gotta really make sure you understand this. You gotta make sure you understand this, because when you move on to the next part, it's gonna include this.
yeah, this is actually one of the more important things to understand. Inductance and capacitance, inductive reactance, capacitive reactance. Okay? And the resonance. But I think we've gotten there. One of the things we deal with these magnetic fields is in electric motors, eh? And it's very important to understand how a magnetic field creates a current in the opposite direction. Because a motor, when it's turning, it's being turned by those magnetic fields. But those magnetic fields are cutting the coils in the rotor or the armature, depending on whether it's AC or DC, and it creates what's called the counter EMF, which is the current in the opposite direction. And that's very important in a motor to understand that. These things also give you a time factor, but that's beyond the scope. It's very important that you understand counter EMF, that you understand inductance, that you understand capacitance. And I think you got there.
Okay. Well, looks like we're gonna end early today. Got 15 minutes to go, but.
If I do this again, I'll have a better idea of where to go with it. Unfortunately, like, I'm at home and I'm reading this stuff that I was given. And